Hello friends, welcome you all to the 52nd lecture on function analysis and its applications. In this lecture, we will discuss the Hahn-Banach theorem, part first. Content of today's lecture is as follows. Hahn-Banach theorem for the real normed linear space. Hahn-Banach theorem. Let M be a linear subspace of normed linear space N, and let F be a bounded linear functional defined on M, then F can be extended to a bounded linear functional F, defined on the whole space N such that norm F is equal to norm small f. Okay. In this lecture, we will discuss the lemma for real normed linear space. Okay. The rest part of this theorem will be discussed in 53rd lecture. So let us start the first part when normed linear space is real. Let M be a linear subspace of normed linear space N, and let F be a functional defined on M. If x0 is not an element of M, and if M0 equal to M union singleton set x0, it is defined as x plus alpha x0, such that x belonging to M and alpha be real, is the linear spawned by M and x0. Then F can be extended to functional f0 defined on m0, such that norm f0 is equal to norm f. Okay. So, proof of the lemma. We prove the lemma for real and complex normed linear spaces. Normed linear spaces separately. Case first, let N be a real normed linear space. Okay. So here in the statement of Hahn-Banach theorem, M be the linear subspace of normed linear space N. Suppose this is the normed linear space N, and let F be a bounded linear functional defined on M. Okay. So let N be the normed linear space and M is the subspace of N. Let F be a bounded linear functional defined on M. F linear functional F defined for subspace M, and this can be extended to a bounded linear functional capital F defined on the whole space N such that norm of F is equal to norm of small f. Okay. To prove this theorem, first we prove the following lemma. Lemma divided in two parts when the real normed linear space and complex normed linear space. So first case we discuss here. Let N be a real normed linear space. Since x0 belonging to M, that is x0 is the element of N minus M. Suppose here this is the N, capital F defines the functional for whole space N, and M is the subspace of N and functional small f defined for space N. Okay, let any point x belonging to N. Okay, and x0 is not element of f, that is x0 is the element of n minus m, that is suppose here x0, x0. Okay, since x0 is not an element of m, that is x0 is the element of n minus m, each vector w is the element of m0 is uniquely expressible in the form w is equal to x plus alpha x0 with x belonging to n. Defined f0 on m0 by setting f0 w, f0 or w equal to f0 of x plus alpha x0, because here w is x plus alpha x0. So f0 is functional, that is we can write this f0 x plus alpha f0 of x0. Okay, so f0 of x0 is r0, this is scalar. Okay, so we can write f0 x plus alpha x0 is equal to f of x plus alpha r0. Why here fx? Because here f0 x, but x is the element of n. Okay, so for x belonging to m, f0 x is fx, because functional f defined for m. Okay, if x belonging to n, then f0 x is fx. Here r0 is any real number. We show that for each choice of the real number r0, f0 is linear on n0, and norm f0x is equal to norm fx. Let us prove. Let beta gamma belonging to R and xy belonging to M, then f0 beta x plus alpha x0 plus gamma y plus alpha x0. Okay, because here vector x plus alpha x0 for m0. So to prove linearity for m0, we have to take vector in m0. So now f0 beta x plus alpha x0 plus gamma y plus alpha x0. Okay, so this can be written as f0 beta x plus beta alpha x0 plus gamma y plus gamma alpha x0, this one. Okay, so this can be written as f0 beta x plus gamma y plus beta alpha x0 plus gamma alpha x0. So here alpha x0 common, so we can write this is beta plus gamma into alpha x0. Okay, so this part can be written as like this, equal to f0 beta x plus gamma y plus beta plus gamma alpha r0. f0 beta x plus gamma y can be written as f of beta x plus gamma y, because here x defined for m and functional for M define F. Okay, so F0 beta x plus gamma y can be written as f of beta x plus gamma y, because here xy is the element of M. Okay, so f is linear. This can be written as beta fx plus gamma fy. That is beta into f of x plus gamma into f of y, plus beta alpha r0 plus gamma alpha r0, because here f0 x0 is r0. Okay, so we can write. So we have this one. Again, this can be written as beta into fx plus alpha r0 plus here gamma common fy plus alpha r0. Okay, again x and y belonging to M, and here x alpha r0. Okay, so this can be written as fx plus alpha r0 as beta f0 x plus alpha x0. Okay, plus gamma f0 of y plus alpha x0, because f0 is defined for m0. Okay, and vector for m0 is defined x plus alpha x0. This shows that f0 extends f linearly on m0. Okay, now we prove that norm f0 is equal to norm f. This is obvious when alpha is equal to 0. Okay, when alpha and beta is equal to 0, that is the case of M. Okay, so case is obvious. Now for alpha not equal to 0, we have norm f0 is equal to supremum of mod f0 x, such that x belonging to m0 norm x less or equal to 1. Okay, so here x belonging to m0, f0 is functional for m union x0. Okay, so this is greater or equal to supremum of f0 x, such that x belonging to m norm x less or equal to 1. Okay, since m0 is superset of m. Okay, that is m is proper subset of m0, or we can say that m0 is superset of m. So x belonging to m0. Okay, so this is the bigger space than m. So this is greater or equal to supremum of m0 x, such that x belonging to m norm x less or equal to 1. Okay, so this definition, if x belonging to m, then f0 x is fx. Okay, because f0 is equal to f on m. So you can write this supremum of fx such that x belonging to m norm x less or equal to 1. This can be written as norm f. Therefore, norm f0 greater or equal to norm f. Okay, thus norm f0 greater or equal to norm f. Equation 1. Next to prove norm f0 less or equal to norm f. Here norm f0 greater or equal to norm f. Now we prove norm f0 less or equal to norm f. Then we conclude norm f0 is equal to norm f. Let us prove it. Norm f0 less or equal to norm f. We first observe that for any x1, x2 belonging to M, we have f of x2 minus f of x1 equal to f of x2 minus x1. Okay, we can write because f is linear functional. Okay, so here f of x2 minus x1. So this is less or equal to mod f of x2 minus x1. Okay, here mod value, so this is only positive. So we can write this one less or equal to mod f of x2 minus x1. Since f is linear functional, so we know that if f is linear functional, then mod fx less or equal to norm f norm x. So by this property, this can be written as norm f into norm x2 minus x1. Okay. Here we have added x0 and subtracted x0. There is no change in this norm value. So using triangle property of norm, this can be written as less or equal to norm f into norm x2 plus x0 plus norm minus x1 plus x0. Okay. This expression can be written as norm f into norm x2 plus x0, and this can be written as norm f into norm x1 plus x0, because norm alpha x equal to mod alpha norm x. Here alpha is -1, that is mod -1, that is 1. Thus this less or equal to this. Thus this can be written as minus f of x1 minus norm f into norm x1 plus x0. Okay, this term left side and this is right side. So we can write minus f of x1 minus norm f into norm x1 plus x0 less or equal to minus f of x2 plus norm x2 plus x0. Since this inequality holds for arbitrary x1 and x2 belonging to M, we see that supremum y belonging to M minus f of y minus norm f into norm y plus x0, and right side can be written as infimum y belonging to M minus fy plus norm f into norm y plus x0. Okay, so we can write, because here x1 x2 belonging to M, this and this can be written as supremum of y belonging to M minus f of y, and right side infimum y belonging to M minus f of y, and x1 replace y and here x2 also by y. Okay, choose R0. Okay, this is R0. Choose R0 to be any real number such that this less or equal to R0 less or equal to infimum of this. Okay, it follows that minus f of y minus norm f into norm y plus x0 less or equal to R0, and this R0 less or equal to minus fy plus norm f into norm y plus x0. for all y belonging to M. With this choice of R0, we shall prove norm F0 less or equal to norm F. Let W is equal to x plus alpha x0 be an arbitrary vector in M0. Okay. Putting y is equal to x by alpha in inequality 2. Okay. This one, inequality 2. So, here y is equal to x by alpha. So, this can be written as minus f of x by alpha minus norm f norm x by alpha plus x0 less or equal to r0 less or equal to minus f of x by alpha plus norm f into norm x by alpha plus x0. Okay. So, if alpha greater than 0, then the right hand inequality in 3 gives, we simplifying this. Here f is linear functional, okay, on M. So, this can be written as minus 1 by alpha fx, and this one alpha LCM, so x plus alpha x0 by alpha, here alpha be scalar and greater than 0, then applying the property norm alpha x equal to mod alpha norm x. Okay, so alpha we can write outside the norm. Simplifying this by cross multiplication of alpha, so this can be written as fx plus alpha r0 less or equal to norm f into norm x plus alpha x0. Okay, so here x belonging to M, here alpha r0, r0 is f0 of x0. Okay, so it can be extended for M0, that is we can write this f0 of x plus alpha x0. Okay, because r0 is equal to f0 of x0. Okay, so we can write this, and x plus alpha x0 is W. Okay, so this can be written as mod f0 W less or equal to norm f into norm W. Okay, equation 4. If alpha less than 0, we use the left hand inequality in equation 3. R0 greater than minus f of x by alpha minus norm f into norm x by alpha plus x0. Okay, again here f is linear functional, so we can write this is minus 1 by alpha fx minus norm f into mod 1 by alpha into norm x plus x0 alpha. Okay, so here mod 1 by alpha and alpha less than 0, so value of this is minus 1 by alpha. Okay, so minus 1 by alpha and here minus, so we can write this is plus 1 by alpha. Okay, so this can be written as minus 1 by alpha into fx plus 1 by alpha into norm f into norm x plus alpha x0. Okay, because we know that mod x equal to x if x greater than 0 and this is minus x when x less than 0. We now multiply both sides of the above inequality by alpha. Okay, that is by cross multiplication and simplifying this. Since alpha less than 0, the inequality will be reversed. Okay, so this inequality will be reversed after multiplication. Hence we obtain alpha R0. Okay, alpha R0 less or equal to minus fx plus norm f into norm x plus alpha x0. This one. Simplifying this, we can write this. This implies that fx plus alpha R0 less or equal to norm f into norm x plus x0 alpha. Okay. Again here R0 is equal to f0 x0. Okay. R0 is equal to f0 x0. So this can be written as alpha into f0 x0 and here x belonging to m. So here R0 is equal to f0 of x0. So this term can be written as f0 x plus alpha x0. Okay, so here x plus alpha x0 is w. Okay, so we can write this is f0 w less or equal to norm f into norm w. Thus we have seen that when alpha not equal to 0, then f0 w less or equal to norm f into norm w. Okay, because here we have proved alpha less than 0 and here we have proved for alpha greater than 0. So we have proved f0 w less or equal to norm f into norm w for alpha not equal to 0. Okay. Now replacing w by minus w in equation 5. So we can write this f0 minus w less or equal to norm f, norm minus w. Okay, so f0 is linear functional on m0. Okay, so this can be written as minus f0 w less or equal to norm f into norm w. Okay. Now from 5 and 6 we conclude that here from 5 f0 w less or equal to norm f into norm w. And here inequality 6 minus f0 w less or equal to norm f norm w. Okay. So from inequality 5 and inequality 6 we conclude that mod f0 w less or equal to norm f into norm w. Okay. So using this definition of bounded linear functional, norm f0 is equal to supremum of mod f0 w upon norm w, where w belonging to m0. So inequality 7 divided by norm w. So we get mod f0 w upon norm w, that is norm f0 as per this definition, and right side norm f. So from 1 and 8 we finally obtain norm f0 is equal to norm f. Okay. Here norm f0 less or equal to norm f, and in equation 1 In one, norm f less or equal to norm f0, and here norm f greater or equal to norm f0. Okay, so we finally obtain norm f0 is equal to norm f. This proves the lemma for real normed linear space. The proof of lemma for complex normed linear space and the proof of main theorem of Hahn-Banach theorem will be discussed in lecture 53. In this lecture, we have discussed the proof of lemma for Hahn-Banach theorem to the real normed linear space. These are the references which have been used in this lecture. Function analysis, Dover publications, written by George Beckman and Lawrence Inercy. Second, introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by V.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.